We will complete the proof of the pumping lemma for context free languages. Recall the statement of the lemma. Basically, it says that suppose L is a context free language, then there is a constant n which depends only on the language L, such that for all strings z in L, such that the lengths of these strings are greater than or equal to n, you should be able to break up this z in 5 parts u, v, w, x, y, such that both v and x cannot be empty. In other words, length of the string v x, that is greater than or equal to 1, length of v w x altogether is less than or equal to n, where this n is the pumping lemma constant for the language L, and then the pumping condition that for all I greater than or equal to 0, that u v to the power I, that means I copies of v followed by w followed by I copies of x followed by y. This string is also in the same language L. Last time we really completed the main crux of the proof, which is showing how this condition 3 we managed to obtain for a certain breakup u, v, w, x, y. What was left was to show that this condition 2, that is the length of v and x is greater than or equal to 1 and v, w, x together, their lengths, all the concatenation of v, w, x, the length of that string is less than or equal to n. This particular part was left, otherwise we had completed the proof. Let us complete the proof by showing that the proof that we gave, it is such that this condition 2 will also hold. Now, very briefly what we did was, first of all we started with the assumption, of course, that is given, that L is a context free language, and therefore we said that let G be a Chomsky normal form grammar for L. Then we said that let G has, or let G, this grammar G, let it have m non-terminals. Next, what we did was, using this value of m, which is the number of non-terminals of the context free of the Chomsky normal form grammar G of the language L, we defined for us the pumping lemma constant. We said let n be 2 to the power n. Okay. Then we said consider any string whose in the language Z whose length is greater than this number. So, we said that let, and then we considered the derivation tree for such a string Z, right, and Z is greater than or equal to n. Remember, n is 2 power n. Then we said look at the longest path in this derivation tree. Okay. Now, we proved a small fact which showed that this path, longest path, length is at least m plus 1. right. So, once I have the longest path in the tree starting from the root node, which is the start symbol S, and of course, going to a leaf node which is labeled with a terminal, we know that this path has length at least m plus 1. We proved this fact. Then what we did was we started going up from in this, we started from here, the end of this path, and going up till we found a non-terminal which got repeated. And again we argued that this case must happen, that is, a non-terminal must repeat. Furthermore, the argument that we gave also clearly showed that by the time you move up m plus 1 edges, one non-terminal must repeat. So, this length of this path cannot be any more than m plus 1. Okay. So, is this clear? What I am saying is that we started from this point. First of all, we said look at the longest path. This path, of course, has to be of length itself greater than equal to m plus 1, but it could be in general much larger than m plus 1, because your z can be very large, and then you are considering the longest path. But now you are going up from the bottom of this path till you find the first non-terminal which has occurred earlier in the path as you go from below. And the reason that we gave, some kind of pigeonhole principle argument, that this repeat must occur by the time this path is of length m plus 1 or less, right. And then we said that, look, remember we said that suppose this particular A derives this part of the string and this second A derives this part of the string, and this part we identified as W, this part we said is V, this part is U, this part is X, and this part was Y. So, this is how we would break up the string. Will it is clear, right, that S of course derived the whole string Z, which is U, V, W, X, Y. Further, A derives this string V, W, X. First of all, I can see that A derives this part, A derives this W part. So, A derives W, and if you think in this manner, the derivation tree of A is, you think of this. So, it is generating, we argued all this last time, that A I can see to be deriving also V A X. And now it is easy to see, and they see this fact is very clear from the diagram itself. And now it is very easy to see, suppose this condition is not true. That means length of V x is 0, it has to be something, length cannot be anything other than anything negative. So, if it is not greater than equal to 1, then this V x length is 0, which means both the strings V and X is empty, right. So, what it means is, if V x length is equal to 0, then this of course implies both V and X are empty, and in that case this particular derivation would mean that A derives A, right. But that is not possible because the grammar is a Chomsky normal form grammar. Remember, for this to happen, we need to have either epsilon productions or unit productions or both, right. I mean, either some unit productions such that A derives A, or some epsilon productions such that some non-terminals get rewritten as epsilon, and starting from A we get only A back. But these cases are not there because our grammar is Chomsky normal form grammar. So, if we assume that both V and X they are empty, then we get a contradiction because that can't happen as the grammar is Chomsky normal form grammar. So, therefore, we say that we can see that this condition therefore must hold, and the other condition is what? We said that length of V W X is less than equal to n. But what is V W X? Now, what is V W X is derived by A, right, and this is the derivation tree. This part is the derivation tree for V W X. In that, the longest path is the path from here to this. See, that is clear, isn't it? Because here there cannot be any path which is longer than this, because then the original path which we said is this is the longest path, that could not have been the longest path in the big tree. So, this is the as large a path as possible in this derivation tree, and we know, that is how we argued, that this path length is no more than m plus 1. See, let us not get confused by this statement. This was about the overall tree, and then when what we said was that we are going down from here up, and by the time we go up, no more than, by the time we get no more than m plus 1 edges, one non-terminal must repeat. So, we are waiting till the first non-terminal. So, this path length, so how shall I write it? So, let us just say this path is theta. So, length of theta is less than equal to m plus 1, and theta is the longest path in this derivation tree starting from A, right. That means what? We go back to our old fact that suppose I have a derivation tree where no path is greater than m plus 1, then the string that is generated cannot be of length greater than 2 to the power m plus 1 minus 1, which is equal to 2 to the power m, which is of course equal to the pumping lemma constant, right. So, let me write it so that it is clear. Length of theta is m plus 1. So, the string VWX cannot be of length greater than, this, which is equal to 2 to the power m, which is equal to n, where n is the pumping lemma constant, right. So, we have said the length of the string VWX cannot be greater than cannot be of length greater than this, strictly greater than this. Therefore, length is less than equal to n, and that is the other condition. So, right. So, we have proved this also and this, and therefore, the proof of the lemma is complete. See, this is something we must appreciate, and this kind of thing was there for our pumping lemma for regular languages as well. What we are saying is that this lemma conditions, they are necessary but not sufficient to prove a language to be context free. In other words, that suppose you find a language L which satisfies all these. From there you cannot conclude that the language is context free. In other words, what does it mean? That it is possible that some non-context free languages also to satisfy all these conditions. That is what we mean when we say that these conditions are necessary. In other words, of course, as the lemma states, every context free language L, they will satisfy these pumping lemma conditions. But the other way is not true. Just because for a language all these conditions hold, you cannot conclude the language, that language L to be context free. In fact, so let me make this point once more, that what it means is that it is not always possible to make use of this lemma to prove a non-context free language not to be context free. So, such an example let me give right away. This is a well known example. L1 is AI BJ CK DL such that either I equal to 0 or J is equal to K is equal to L. So, what it means is that when firstly this language L1 has a string of A's followed by B's followed by C's followed by D's, where either there are no A's, or if you have a number of A's, then it must be the case that the number of B's is equal to the number of C's equal to the number of D's. Now, this language is not a context free language, but you see that it will satisfy all these conditions. Why? Suppose there are two cases, either I equal to 0, then there is no really restriction on JKL, right. So, basically we have consider a string like B, J, C, K, D, L, and let us say the entire VWX part occurs within B, and then you pump. So, number of B's go up or one B goes down, so that is okay, right. This is still in that form, because we cannot add any A's in front by pumping up or down, right. So, we will remain within the language L. On the other hand, suppose I have some A's followed by B's. So, let us say this is R, then it must be the case, if since I have a number of A's, C R and D R, these number of occurrences of B must be equal to number of occurrences of C's and as well as for D's. Now, again it is possible, if you take such a string from the language, then your VWX can very well be within this, right. You can choose your u v w x y such that v w x part entirely is within A's. So, when you pump up or down, all that happens is that you change the number of A's, but number of B's, C's and D's do not change, and therefore, on pumping the string that you would get will be also in the same language L1. So, the point I am making is that this is a language L1 which satisfies the conditions of the pumping lemma, and yet L1 is not a context free language. So, let me write it down. L1 satisfies the conditions of the lemma, but is not context free. And we will be able to prove that this language L1 is not context free language by some other means, but not by using this form of pumping lemma. There are stronger forms of pumping lemma, in particular one stronger form which you can use, which is fairly well known and used, is called Ogden's lemma. Is a stronger form, but will not discuss Ogden's lemma here, or there are other versions. Even Ogden's lemma will not be able to prove some languages to be context free. Then in fact, we gave one reference while discussing for regular languages, and that reference, that paper contains the most general form of pumping lemma for context free languages. Here are some examples, some more examples of languages which are not context free, and all these three languages you can prove that they are not context free by using the pumping lemma that we have seen. Now, just a little discussion on the form of these kinds of languages, and at least intuitively you should be able to appreciate certain things or certain properties which context free language cannot ensure. See, here what is happening? There are three strings A, B and C. What you want is, first of all, that B and C, they must be equal in length, and length of A is less than equal to length of either of these. Now, if you let us say remove this, right, then it will be a context free language, but adding this is the problem. See, what you will see later when we discuss the machine version, that it is easy to ensure this or this, but together it will not be easy for a context, it will not be possible to ensure both these constraints at the same time. These are, intuitively I am trying to explain to you, and similarly if this is not there, this condition, of course we can ensure, we can write a context free grammar which will generate this language B and C n such that n is greater than equal to 1, there is no m. Right? But together both these conditions we cannot handle using the context free nature of the grammar that we have. Take another kind of thing, similar things, you see, again there are these two condition business, that I is less than equal to j and j is less than equal to k. the problem is that once you ensure this, again you see this one of these was not there, either A or this or either of these letters, then again we can ensure that by means of a context free language. In other words, supposing A was not there, BJCK such that J is less than equal to K, this is something we can handle. We can write a CFG, context free grammar, to generate such strings, but these two conditions together we cannot handle. Now, another version of the same two condition business is, now I should say that you should also realize, in fact let me say what I want to say after I discuss this. What is this? Again I have two conditions, right, that number of A's must be equal to number of C's and number of B's must be equal to number of D's. Two conditions. Again this is something we cannot take care. Again, if you look at pumping lemma, why that is the case? Where is, you can say pumping lemma constant is, let us say, K, then you take a string AK, BK, CK, DK, right? And then what happens is that the window VWX will be either entirely within one of these letters, strings of one letter, like entirely within A's or B's or C's or D, or can straddle two consecutive ones. So, what will happen is it will change the lengths of two consecutive ones at most, but here we need to make sure that the lengths of the first and the third they match, and that is where the problem will happen. The same way that we had proved for that language A N, B and C N not to be context free language, same kind of proof idea will go through here too. But I am somewhat incorrect by saying that we cannot handle two conditions. We can handle two conditions so long they are not kind of intermixed or together. So, for example, if you take another language L5, let us say I write it slightly differently, AM, BM, CN, DN. This is context free, right? How will you do that? Remember, I can separately generate this from some S1, separately generate this, and these are just the two concatenations. In other words, what will be that grammar? So, we can start with S goes to S1, S2, right, and then S1 is A S1 B or AB, and S2 is C S2 D or CD, and you can see that this grammar is going to generate this language, right. So, we can handle two conditions, but not together. Is that clear? Or this is really intuitive way is what I am explaining. And whenever you see that the conditions have to be kind of there mixing up, or both the conditions you need to ensure together, that is where the problem arises, right. So, you should be able to at least intuitively see that the situation with L2, L3 and L4 is different from L5, or for that matter L6, which is AM, BN, CN, DM. Right. Here I need to keep track of correspondence between A's and D's separately from the correspondence between B's and C's. This is something we can handle so long. So, what is the difference between this and this? As you handle this, M is number of A's here is equal to number of C's, there I am getting some B's inside, and you see that is where the problem will happen. We'll kind of be able to appreciate this a little more, whereas here this I can handle. I have generated some A's, and this is taken care of and separate. I mean, best is you should yourself write the grammar for L6. This is a context free language. So, you will be able to again very simply write a context free grammar which will generate this language. Well, now that we have the pumping lemma, and we know in particular one language, several languages which are not context free. Now, using that fact, I can come to a very strong conclusion, right. So, let me show what that conclusion is, that the class of context free languages, this class is not closed under intersection. We will just now, a little later, we will talk about the other closure properties, but this kind of immediately, almost immediately follows from whatever we have been discussing. So, recall what does it mean to be, for a class to be closed under intersection? We are talking about classes of languages. So, each language is a set. I take two elements. So, one language and another language L2, and I create the intersection of these two. We say the class is closed under intersection if whenever you pick up two languages from here, from within the class, take their intersection, the result is also within that class. But we will be able to show very easily that this is not the case with context free languages. So, let us take two languages L, AI, BI, CJ, and L dash, AI, BJ, CJ. So, claim, which we can easily prove, that both L and L dash are context free. So, let me quickly give a grammar for L. For L, you can let me show you the productions. S goes to, let us say, X, Y, okay. X goes to A, X, B, A, B, and Y goes to C, Y, or C. So, you see, basically Y can generate any number of C's, and X will generate equal number of A's followed by B's, right. So, X will generate a string of A's and B's, where number of A's will be equal to number of B's, and Y will generate just any number of C's, and your string S is the concatenation of these two. So, therefore, you will generate all strings of the kind which is mentioned here. And in a very similar manner, you can also give a grammar for L dash. But what is the intersection of L and L dash? So, obviously, they have to be again of the form A's followed by B's followed by C's. Since they are in L, all these strings in the intersection strings are in L. So, the number of B's must be equal to number of A's must be equal to number of B's. Since the same string is also in L dash, that means number of B's also must be equal to number of C's. So, therefore, A's is equal to number of B's equal to number of C's. So, this is in fact this language N, Bn, Cn, n is greater than or equal to 1. So, as you see, a very important result we proved quite easily from the fact that this language is not context free, and this particular language is the intersection of two very simple context free languages. So, the class of context free languages, this class is not closed under intersection, because I could find intersection of two context free languages, which is A n, B n, C n, which we proved by pumping lemma, which is this language is not context free. This situation, as you know, is very different from the situation of regular languages. Regular languages are closed under intersection, right. So, since we are talking of closure, we might as well see some closure properties of context free languages. So, first point, which is again fairly simple to see, that class of CFLs is closed under union. Why? You see, what we are saying, that you take two languages which are context free languages, then take their union L1 union L2, and we are claiming that that union language will be context free. So, this is very simple. So, let us say, so let me give the proof with let L1 L2 be context free, and generated respectively by G1 and G2. So, in particular, let us say G1 is Vn1, P1 S1, and G2 is right. Now, assume that we can, if need be, by rewriting some, by renaming some of the non-terminals, assume that these two sets Vn1 intersection Vn2 is empty. That means, we do not use the same name for two non-terminals from these two grammars, right. And now, you see, think of another grammar which is like this G, which is a new start symbol S union. So, I should put it in braces. So, basically just take the union of this Vn1 and Vn2, add S to that. So, that make it your new set of non-terminals union Vn1 union Vn2, right. This is the set of non-terminals P, of course sigma P, and this new non-terminal is your start, and basically your P is P1 union P2 plus one more, and which is that P is P1 union P2 union just one more production, and that is S goes to either S1 or S2. So, what is happening? You start this grammar G with the symbol S, and this S can be rewritten as either S1 or S2. If you rewrite as S1, you will generate a string of use the grammar G1 to generate any, you can generate any string of L1. Similarly, you can generate, if you first rewrite S by S2, then you can generate any string of L2. So, therefore, together it means that from S you can generate all strings of S1 as well as all strings of language L1 as well as all strings of the language L2, which is precisely what the union language. So, therefore, the class of CFLs, this class is closed under union. So, from these two which we have just proved, we can conclude something very important, another property, closure property, that class of CFLs not closed under complementation. Remember, complementation is that language L is there, you take the complement, and the complement language is sigma star, that the alphabet minus language L, right. The set of all strings over sigma which are not in the language L, that set is the complement of L. So, what we are saying is, it is possible that you take a CFL, context free language L, you complement it and you get a language which is not context free. Or similarly, it is possible that you take a not context free language, take its complement, and it may turn out to be context free. So, see, point I am making is that this 3 actually follows from 1 and 2. Why? Because I can write intersection of two languages L1, L2 as, take the language L1, complement it, take the language L2, complement it, take the language their union, right, and then complement the entire thing. This is just a set theoretic way of expressing intersection in terms of union and complementation, right. Essentially, it's, those of you know, it's a kind of De Morgan's law. So, L1 intersection L2 is this. Now, suppose the class of CFLs where, this class was closed under complementation. So, now suppose L1 and L2 are context free languages. If the class was closed under complementation, then this will be a context free language, L1 complement, L2 complement is another context free language, you are taking their union, which is union we know is preserves context freeness. So, then this whole thing will be context free. Again you are taking a complementation of a context free language, which by assumption would be again context free. So, then what would it mean? That L1 intersection L2 would be also context free. So, in other words, what I am saying is, if complementation, if class of context free languages, this class was closed under complementation, along with the fact that this class is closed under union, we would get the class is closed under intersection. But we know this class is not closed under intersection, therefore, and we also know it is closed under union. So, what is the possibility left? That it is not closed under complementation, right. So, that is how we prove 3. There are other closure properties which we can very easily see. We talk of 2 other things often, which is concatenation. So, we will say, in fact, this we can prove again, these 2 things, class of CFLs is closed under concatenation, and class of CFLs, this class is also closed under Kleene star. Okay. Remember that what is this is a unary operator, whereas this is a binary operation. So, we take 2 languages L1 and L2, and this is the concatenation language. Remember that L1, L2 is nothing but U V, such that concatenation of U and V such that U is in L1 and V is in L2, right. Again, this is very easy to see that class of CFLs is closed under concatenation. Why? Because for L1 you have a grammar, L2 you have a grammar, both are context free grammars, and they have 2 separate something what we used for union, same idea will use that. Suppose G1 is the L of G1, the language generated by G1 is L1 and the language generated by G2 is L2, right. And let us say G1 is Vn1 sigma P1 S1, G2 is Vn2 sigma P2 S2, and the new grammar for L1 L2 will be a G, which is will obtain by taking the unions of Vn1 and Vn2, assuming that they are disjoint. You can understand why I want them to be disjoint, because otherwise the derivation of one will interfere with the other. And we will add a new start symbol S, and that will write it as, we will just add this production and rest of the productions will remain G1 and G2, right. So, you can easily see that if we start with this S, we generate S1, S2, S1 and S2 are the start symbols of G1 and G2. So, through S1 I can generate any string of L1, with S2 I can generate any string of L2, and therefore, I can generate the concatenation language. Kleene star was, if you recall, we used it extensively in case of regular languages. There was a language L and Kleene star was that star operation. So, what was it? Very briefly, L star is the set of all strings obtained by taking 0 or any number or concatenation of any number of strings from L. Okay, that will you will remember what it was. Now, L star, so basically L star is a CFL if L is a CFL. This is the meaning of 5, right? And again, that is not very difficult to see, that suppose L is generated by G, where the grammar is Vn sigma Ps, right. So, all we have to do is to just add one more production. So, basically, sorry, I should not have said this way. So, I should have said G, suppose G is this, such that Lg is L, then for L star the grammar is G1, right, which is just you add one more production P union, just add this production. So, keep the same start symbol, S goes to SS or epsilon, right, and you can easily see that LG1 is L star, right, because you see then now starting from S you can generate any number of copies of S, and from each S you can generate a string of L, and that is what would generate the language L star.